Hello, my name is David Kirk, and I'd like to present a video progress report and technical description of my Stirling engine project. A little of my background: I'm a mechanical engineer by profession. I've worked in the internal combustion engine field for all of my 32-year career, and since retirement I've started my own consulting business specializing in internal and external combustion engines. This Stirling engine project started out as a hobby, but has grown into a more dedicated project, and now that I have more time to devote to it, I want to see this through to completion. My goal in this project is fivefold. First, to develop and construct a technology demonstrator Stirling engine that's large enough to produce useful power around 700 watts or 1 horsepower shaft output. I wanted to construct a prototype in the form of a portable generator set that's capable of producing at least 500 watts of electrical power. Second is to use pressurized air as the engine's working fluid versus helium and hydrogen, which are working fluids that have been used in the past in Stirling engines. Third is to use propane as the fuel for ease of development and testing. 4 is to utilize liquid cooling of the engine to maximize the delta T across the engine for maximum power output potential. And 5 is to utilize design methodology to allow for economical mass production when the engine reaches that point. Since the heater head is the most expensive component in a Stirling engine, I've elected to go with a canister type finned internal and external design made of investment cast stainless steel. This would be a one-piece part finished by one simple machining operation, therefore minimizing costs. The design targets I've had in mind are also fivefold. First of all, demonstrate the quiet running, which is inherent in a well-designed Stirling engine. The closed cycle form of operation tends to make the engine extremely quiet. Second is the ease of operation, in that the engine operator would require very little input in order to run this machine. Third is inherently long operational life with minimal of maintenance required. The fourth design target would be high thermal efficiency with very low emissions. The high thermal efficiency is gained by regeneration used in the operational cycle, and low emissions is due to a continuous combustion heat source. And the fifth design target would be a practical power source for certain specific applications, such as a portable generator set as shown in this prototype, or a combined heat and power system for small homes. Now I'd like to give a verbal description of this prototype. The dimensions of the carrying frame are 18 inches long by 9 inches wide by 18 inches high, and the weight is 59 pounds. This engine is constructed and based on a Chrysler SV-2 automotive air conditioning compressor. It forms the basic structure of this engine. This is a V-twin alpha type configuration Stirling, which in my opinion is the most compact form of Stirling engine. It's also the most mechanically simple. There's only 5 internal moving parts. That's 2 pistons, 2 connecting rods, and a crankshaft. And the 90-degree V-twin, properly counterweighted, has inherent primary balance, yielding a smooth running machine, and also it yields the 90-degree phasing necessary for the Stirling cycle. The advantages of using an existing air conditioning compressor is that it's designed for pressurization, plus many of the internal components that are difficult to make are already completed. This simplifies development time and reduces costs. The disadvantage in using a machine designed for a given purpose and converting it to another use always involves some compromises, and we will discuss these as this presentation progresses. The specifications on this compressor are a bore of 58.7 millimeters, stroke 33.4 millimeters, which yields a bore-stroke ratio of 1.76. And this is actually ideal for a Stirling kinematic type machine. The displacement of one cylinder is 90.4 cc's. Now the displacement of the total machine is 127.8 cc's, in that both cylinders in a Stirling cycle engine are communicated via the gas flow duct. The actual swept volume of the machine is the square root of 2 times the displacement of one cylinder. Now the intended charge pressure, as stated previously, is 3 to 12 bar, or 45 to 175 psi. A properly designed Stirling engine of this displacement should be capable of 750 watts shaft output, per the literature. Now I've maintained a lubrication system in this engine that the compressor featured, and that is a pressurized oil lubrication that utilizes a gear rotor oil pump and delivers oil to the crank pin bearings of the connecting rods. This assures long life and quiet running of the machine. The crankcase in this design is used as the buffer space. There is a snifter valve incorporated that communicates between the actual working space and the buffer to maintain a positive pressure bias, and this greatly reduces oil migration into the working space. Now I'd like to describe the individual components that make up this prototype. This is the original Chrysler SV-2 compressor that forms the main structure of the engine block, with the crankshaft and connecting rods. This area is where the gear rotor oil pump is located, and there's an aluminum oil sump that bolts to the bottom of this cast iron block. All of that is retained pretty much unchanged from the original compressor intent. The specialty components that had to be made to convert this to Stirling operation can be seen here on the hot side, or the displacer side of the engine, and the cold side, which is the compression side. Specialty components made on this side include the burner, the regenerator, the heater head, and the cooler, plus adapter plates to allow all of this componentry to fasten to the original compressor block. There's a connecting duct that communicates to the coal side compression cylinder, and a special head was made for interfacing with this duct. And one of the original cylinder heads from the compressor was retained for a coolant passage container. There's a pressure gauge here that registers the buffer pressure, and as I stated before, the engine is air charged and pre-charged with compressed air prior to running. This Schrader valve allows for air to be introduced into the engine via a compressed air bottle. The alternator is a pancake alternator originally designed for garden tractor use. It's 12 volt AC output, and that's rectified to DC by a rectifier that's used. It's driven via a 1-to-1 ratio by a belt from the engine crankshaft. As stated before, the engine is water cooled, and this is an electrically driven water pump that uses some of the alternator output to circulate coolant through both the main cooler. And the compression side water jacket. The clutch normally used in automotive compressor applications has been dispensed with, and a special flywheel and starter pulley have been made for the Stirling engine application. And you can see the belt position here that drives the alternator at a 1-to-1 ratio. This is the Chrysler SV-2 compressor crankcase. It's a cast iron casting and it's quite heavy. One of the design compromises that I mentioned earlier would be to make this out of a cast aluminum versus cast iron, because this is designed for very high pressure use as a refrigeration compressor. It would be totally unnecessary to design for a Stirling engine using this heavy of a wall casting. This is the main bearing housing for the crankshaft. Some of these internal passages are not used in the compressor to Stirling conversion. Cylinder bore can be seen. This is the location for the gear-rotor oil pump that supplies lubricant directly into the crankshaft. And the base machined face where the oil pan bolts to. This is the crankshaft for the compressor. Has a ball bearing, main bearing on the output side. Extremely beefy and designed for heavy-duty use. For a dedicated Stirling engine, the crankshaft would not have to be as robust as this piece. The opposite side main bearing is a plain bearing where oil is introduced into the center here for crank pin lubrication. And you might be able to notice that the crank pin is actually drilled for direct lubrication of the connecting rod bearings. The connecting rods used in this machine are actually Alcoa aluminum forgings, very heavy duty and much over-designed for a Stirling engine operation. Nevertheless, these parts are already machined and ready to go, so that simplified a lot of the machining that I had to do in making this engine. Here's the piston that's used in the cold side of the engine, the compression side. As you can see, the distance from the wrist pin center line to the dome of the piston is very short, and this was done in the original design of the compressor just for compactness. But this short dimension only allows use of one piston ring. And so I'm using cast iron piston rings with an internal expander, which has provided actually excellent sealing for converting this to Stirling operation. The piston has also been drilled for oil return, and it's an aluminum casting. These were specially made pistons made from the original compressor parts used as a pattern. New pistons had to be made mainly to get a tighter clearance, cylinder wall to piston skirt, for quiet running. This is actually the displacer and piston assembly used on the hot side of the engine. The displacer is made of thin wall 302 stainless tubing with a hemispherical crown welded in place. The displacer bolts to the piston via two fasteners that join from underneath. There is a thermal isolating gasket used between the displacer and the aluminum piston just to minimize heat transfer. You can see that one of the compromises in this conversion is the very short skirt supporting this rather long and somewhat massive displacer. In a dedicated design, this side of the engine, in other words the hot side cylinder, would be made longer, and correspondingly this piston skirt would be made longer as well to better support this cantilever load. Although this piston is very short, it's provided actually good support and has shown virtually no wear in the testing that I've done thus far. This shows one of the special piston ring designs that had to be made for this compressor to Stirling conversion. The reason being that gap losses and leakage on a conventional piston ring will not work and drastically reduce the performance of a Stirling engine. So these special design piston rings were made that utilize a step gap. These are cast iron, and an expander is used behind the ring for radial pressure against the cylinder wall. This is the heater head used on this Stirling engine, and for prototyping this was made in 3 separate pieces. There's the dome, hemispherical shaped dome that was machined from a solid billet of 316 stainless steel. The cylindrical portion of the heater, which consists of a finned ID and finned OD surfaces, and the lower flange, which was turned and welded into place. The cylindrical portion of this heater head was made by the wire EDM process and made from a solid billet block of 316 stainless steel. As stated before, this would be an excellent candidate for a lost wax casting process, and the material used would be a higher nickel content stainless steel to improve thermal conductivity. This is the cooler assembly. It's made of an aluminum alloy, and the internal finning is also wire EDM'd to shape. The outside is turned to form a depressed surface with 2 O-ring grooves, and a cylindrical aluminum turning is pressed over this that forms the water jacket. In production, this would be an easily made part from an aluminum extrusion. This is a sample of the regenerator material used in this engine. It's 1/1000 thick by 1 inch wide stainless steel, 302 stainless ribbon that's wound to form an annular coil by which the working fluid passes through. The spacing of each individual wrap is accomplished by using a seamstress wheel and dimpling the surface of the foil such that about a 5/1000 of an inch spacing is achieved from wrap to wrap. This is a trick that was kindly given to me by Andy Ross, who is one of the experts in the Stirling engine field. One of the considerations for good performance from a Stirling engine is to close couple all of the thermodynamic components, and by that I mean the heater, regenerator, and cooler are all in close proximity to each other and all on the displacer side of the engine. This is a very important design consideration that's really not stressed in the literature, but I've found through experimentation that the close coupling of these components really works well to help overall performance and efficiency. The other thing is the design to thermally isolate these components from one to the other, and then the total stack from the engine structure is also important. This reduces conductive heat losses into the structure, which ultimately will hinder the full performance potential. The design of this particular assembly is done by a stack of the heater, regenerator, and cooler assembly sealed by O-rings and using the minimal amount of metal-to-metal contact. Also, an adapter plate is used with only 4 bolts compressing a ring that engages with the flange of the heater head, and this design compresses the whole component stack, sealing the O-rings and making for a gas-tight fit. The adapter plate in turn is isolated from the engine structure by thermally resistant gaskets. I'd like to discuss the engineering aspects of a Stirling engine. The physical processes by which heat is converted to work in the Stirling engine are forced convective heat transfer combined with associated viscous dissipation or flow friction of the working fluid. The fluid dynamics involve a repetitive cyclic process of fluid momentum, heat, and mass transfer. Heat transferred into and out of the working fluid is through metallic heat exchangers with known thermal conductivity. Minimizing the internal volume of the heat exchangers is necessary to keep compression ratio as high as possible for good efficiency without detracting from the heat transfer requirements per cycle. The heat exchangers must exhibit low flow losses due to viscous effects. Overall, the problem is extremely complex. Fortunately, there are some design guidelines formulated by experts. One of these is Alan Organ, plus some computational modeling software available. And this is known as SNAP. It stands for Stirling Numerical Analysis Program, and that was written and contributed by Alan Altman. And both of these provide very good guidelines and verification in the design of a new Stirling engine. Estimating realistic operational temperatures of 900 degrees C in the heater and 100 degrees C in the cooler, and a target cyclic operational frequency of 42 Hz or 2500 RPM, and air at 12 bar pressure as the working fluid, the thermal components of the engine now may be designed. Utilizing the guidelines specified in Alan Organ's text, the heater, cooler, and regenerator were predicted. Verification of the complete engine system was accomplished using the second-order computer code, SNAP, by Alan Altman. This predicted a shaft output of approximately 700 watts at the desired operational conditions and frequency mentioned. The specialized thermal components were made by my friend and associate John Archibald, who beautifully crafted these parts from design drawings and sketches. Assembly was straightforward, with no surprises, and initial runs were successful. Although failure of heater head O-ring seal necessitated replacement with a higher temperature material, that was really the only problem initially encountered. Currently, maximum charge pressure has been limited to 100 psi due to lack of higher pressure air source in my shop. I'll be using a nitrogen working fluid in the future at 175 psi for testing, obtained from a high pressure bottle. Nitrogen yields exactly the same operational properties in a Stirling engine as air, and it's much safer to use since it doesn't provide an oxidizer for any type of combustion reaction, since we are using an oil lubricated engine system. A cylindrical inwardly facing flame impingement burner was designed to provide heat using propane as a fuel. The burner is the atmospheric type, requiring no external pressurized air supply. Operation is known as an ejector principle, or a momentum exchange. Pressure ratio across the fuel jet is in the sonic flow regime. This introduces airflow in the mixer tube. The stoichiometric air-fuel ratio of 15.7 by mass for propane dictates the overall mass-flow proportion that's introduced into the burner. Knowing the heat requirement of the burner, the fuel jet size is determined, and all physical geometry of the burner may be calculated. The engine simulation predicts a 25% thermal efficiency of the engine. Thus, the burner must supply at least 4 times this much heat energy into the heater head. At 700 watts desired crankshaft output, the burner must supply 2,800 watts minimum, or 3,200 watts ideally. A computer code was written to design this burner based on the above information, and it has proven valid. Although I must admit I made a mistake in the construction of this burner. There is an anti-flashback screen used behind the flame sheet. The flame sheet is the piece that you see that has all the perforated holes. The anti-flashback screen is utilized to prevent flashback into the burner annulus. The screen has provided an effective reduction in the jet or the hole size in the flame sheet, and thus limiting the burner output to approximately 2,000 watts. Future testing on this project will comprise of the following: correct the burner to allow design thermal output to be met. Also investigate a metallic cloth burner emitting a higher infrared energy into the heater head. Ramp up the charge pressure to the design target of 175 psi using nitrogen. Run performance testing of the engine consisting of 1. Crankshaft measured power output, most likely measured using a Prony brake. 2. Measure electrical power output using a resistive load off the alternator. 3. Measure operational temperature of the heater head using an optical pyrometer. 4. Determine reject heat from the liquid cooling system, knowing the flow rate and measuring the delta T. 5. Calculation of thermal efficiency, engine only, at various speeds and load. And 6. Running some mild endurance testing. To conclude, there are no plans to produce the engine shown here. This is strictly a prototype development project to test the feasibility of a Stirling engine in this particular application. There are no plans to produce drawings or component parts to make this engine because they are much too difficult for the home hobbyist. Pending a successful outcome from the testing of this prototype, the next logical step would be to redesign the compressor portion of this engine to be a dedicated Stirling engine. Finally, investigate the market potential of the product to see if there is any desire for such a product, and then work with manufacturing concerns to actually produce it. Next, we're going to show a running demonstration of this engineering prototype, and I'd like the viewer to pay particular attention to the following points. The engine, after light off, takes about 4 minutes to come up to temperature until self-sustaining operation is possible. Once the engine is running, it takes about 1 minute to attain 1500 RPM at an 80 to 100 psi pressure charge. The cooling system configured is for short runs only. It consists of an open sump surrounding the fuel container. The cooling of fuel, as it's used, extracts coolant heat, but it's really not in proportion such that the coolant continually warms up. That limits runs to a few minutes only. but it does keep the fuel bottle warm and maintains pressure at the discharge jet. Notice that the engine runs very steadily and quietly. The chirping noise heard in the background is not from the engine, but birds actually in the background. The camera is brought up to within 1 foot of the running engine, and it's literally quieter than a sewing machine. A slow leak in the engine necessitates a charge top-off every 15 minutes or so from a 100 psi air source. This leak is most likely from a gasket and will be investigated and repaired. You'll note the slight RPM increase as the engine pressure is recharged. The engine runs for over 2 minutes after the burner is extinguished. This indicates that the regenerator is functioning on design.